In this video, we are going to finish up section 1.1 in your book by talking about functions. So here's how this works. Here's how functions are defined. You've probably seen them before, but let's be a little bit more formal. We're going to let capital X and capital Y be two sets. And then a function f from x to y, we write it with a colon and an arrow like that, is a rule that associates each element little x of our set X to exactly one element into little y of our set Y. And then we call X the domain. And that's pretty consistent. Pretty much everyone uses domain to mean that. The next two words, range and image, exactly what they mean varies from mathematician to mathematician, so every book is going to have to tell you what it means by range and image, but this is what our book means. We call Y the range. So, and we're going to call f of x. So f is a function, but you can take f of a set, and that's just the set of all f's of little x, such that our little x is in the set big X. The image. And we're going to notice that the image is a subset of the range. The image might be a proper subset of the range. There might be some elements of Y that are not f of x for any x, or they might not be. So let's have a couple of examples. We're going to let A be a subset of X. We're going to let Y equal, let's say, the integers, or the rational numbers or the real numbers. Let's use the real numbers, and then this function, chi sub A of x, this function is 1 if x is in A, and it is 0 if x is not in A, is called the characteristic function of A. And then the image the image might be 0 if A is the empty set. It might be 1 if A is all of X. Or it might be the set with two elements, 0 and 1. And that's actually what it usually is for any subset A other than the empty set or the whole thing. And then the range. Notice I was sort of ambiguous about that above. We can view you can think of the range as being the real numbers, the integers, the rational numbers, lots of other things. So if you're given a function in its domain, and those are sort of very natural things, but the range is a lot squishier. It's sort of not clear when you're given a function what the range is supposed to be. And so something else you ought to know about is composition. So if f is a function that goes from x to y, and g is another function that goes from y, the range of f to z, then f composed with g, g composed with f is a function that goes from x to z, and that is given by g composed with f of x is equal to g of f of x. And that's actually going to be one of the most important function operations for us. I know you know how to add functions or multiply functions or all that stuff. What we care about the most is function composition. So now let's have one more definition, and we'll be done with this video. So this is definition 1.1.10 in your book. So we're going to let f be a function from whose domain is x and whose range is y. F is injective if for each y and y there is at most one pre-image. So there doesn't necessarily have to be a pre-image. There could be no pre-images. But the idea is there is no more than one x in x with f of x equals y. So if you know what y is, you know what x is. F is surjective if for each y and y there is at least one x. There is no less than one pre-image. And it is bijective if it is both injective and surjective. So let's write that out precisely. For each y and y, there is exactly an x in x with f of x equaling y. So let's have an example. Let's let f of x be x squared And then let's let n naught be the natural numbers plus 0. So n naught is the set of all non-negative integers. And then f is 1 to 1 on n naught. So it's very important when you talk about a function, you have to take into account what you're thinking of the domain as. The function x squared, which you surely know from high school algebra, it's not 1 to 1 on the real numbers. It's not even 1 to 1 on all the integers, but it is 1 to 1 on the non-negative integers. And let's have another example. Let's let f of x be the absolute value of x, and then f of x is surjective if you view the domain as, let's say, all of the integers and the range as the non-negative integers, but is not surjective if you view the range as being the integers. So whether your 1 to 1 is sort of inherent to just the function and the domain, but we said the range was sort of squishy, or whether you're surjective depends on what range you pick, and sometimes there are many sort of natural ranges. That's why we like to talk about the integers so much. One last thing I want to say. A relation, this is technically a redundant definition. A relation f between sets x and y. We say it is a well-defined function. This just means that it's in fact a function, but so it's redundant. A well-defined function is just a function that's actually a function, but we sometimes use the term well-defined function for emphasis. So it's a well-defined function if it indeed associates each x in x to exactly 1 y and y. And let me give you an example. This comes up a lot when you write down something that looks like a function and isn't. You call that ill-defined. So let's let f that goes from the rational numbers to the rational numbers be given by f of n over d is n squared over d squared. And that is well defined because if you have two different fractions that mean the same rational number, 2/4, 3/6, 4/8, when you square it, you get 4/16 or 9/36 or 16/64. You get something that is well defined. You get the same answer. You put two different inputs in that look the same but are secretly the same input. You get the same thing out. So this is well defined. And here's what I mean by an ill-defined function. We're going to let g be given by, if you would try to define a function on the rational numbers this way, you square the numerator and then you cube the denominator. It looks an awful lot like our function f, like our well-defined function, but this is not well-defined. This is ill-defined. It is trying to say that g of 1/3 is 1/27th, but g of, let's say, 2/6 is 4/216. That's 1/54. And these really ought to be the same thing for a well-defined function. So that's what we mean by ill-defined and well-defined. So in section 1.2 of your book, what we're going to do is we're going to define the real numbers. We're going to rigorously construct something that acts like we expect the real numbers to act like, because we want to nail down, we want to have precise definition of things. And your book doesn't include this, but I think we had better start by pointing out that, in fact, it's pretty easy to put down a rigorous construction of other sorts of numbers, because we're going to need them to construct the real numbers. So we can rigorously construct lots of numbers. All right, so I'm gonna start off with the Peano axioms. This lets us formally define the natural numbers. Which we write with a bold N like this. So here are the Peano axioms. We just declare that 1 is a natural number. It's just this object we've got. And then we're going to declare that every natural number n has what we call a successor, S of n, which is also a natural number. And then we're going to say that the successor function is a one-to-one function. That is, different numbers have different successors. So if m and n are natural numbers, and the successor of m is the same as the successor of n, then m is equal to n. And we're going to flip this around and say that no natural number is the successor of 1, whose successor is 1. So 1 is the first of the natural numbers. And the last of the piano axioms, it's a little bit more complicated than the others, but not by very much, and it's going to do two very good things for us. We're going to let k be a subset of the natural numbers. So we can rewrite some of these rules using n for the set of natural numbers and the inclusion relation. If 1 is an element of k, and if S of n is in k for all n in k, then k is in fact all of the natural numbers. And this does two things for us. If you just start with 1 and throw in the successors, 1 and the successor of 1 and the successor of the successor of 1 and so on, eventually you get all the natural numbers. That's one thing it does for us. So this is saying the natural numbers is 1 and its successors, and that's it. And the other thing this axiom does for us is that it's induction work. And that's 5 very simple rules describing this set of natural numbers. You can throw in a little bit of notation. The successor of 1, we're going to name that 2. The successor of 2, we're going to name that 3, and so on. And from this, from just these 5 rules, we can get pretty much all the properties of the integers. All the properties of the natural numbers. So, for example, we can define addition by the 2 rules. N plus 1 equals the successor of n, and n plus the successor of m is the successor of n plus m. And then that lets us prove, and then there's a lot of work which we aren't going to go into it, but from these axioms you can prove that everything you want about the natural numbers is true. For example, you can prove that addition is associative. And let me show you how that proof works so that you can see how the fifth axiom is indeed induction. So let's let capital K be the set of all natural numbers little k such that you're associative with k. So your last option, n plus m plus k is equal to n plus m plus k. For all n and m, or for fixed m and n and m, it doesn't really matter. And then first let's show that 1 is in k. N plus m plus 1, that's by definition is the successor of n plus m. And then that's from our first axiom in the definition of addition. And then in our second axiom, we can turn that into n plus the successor of m. And that's n plus and then m plus 1. So we've seen that, so 1 is in k. And then let's let some little k be in our set k. And then n plus m plus the successor of k. That is, by our second definition, by our second axiom defining addition, that's the successor of n plus m, then plus a k. And then little k is in our set k, meaning we are now allowed to flip this to n plus m plus k. And then we use our definition of addition again, n plus the successor of m plus k, which is n plus m plus the successor of k. And so if k is in k, so is the successor of k. And then by our piano axioms, our set k is all the natural numbers. And so n plus m plus k is equal to n plus m plus k for all k. So that's how you build the natural numbers out of these two very, very simple pieces, the number 1 and the successor operator, which spits out another number. And if you're willing to put enough work into it, you can improve everything you know and love about the natural numbers just from these simple axioms, similar to how we've just proven associativity. And once you've got the natural numbers, it's simple to construct other numbers we know and love. So, for example, the integers. The integer z, we're going to throw in one other number, 0, and then we're going to throw in the set of all ordered pairs, where one element is a natural number and the other element is either plus or minus. And so all you need to construct the integers are three more symbols, 0 and plus and minus, and the natural numbers which you already had. And then you can define addition and subtraction and multiplication in the integer, or is it carefully enough, you can define the rational numbers. So once you have the integers, you can define the rational numbers. You're going to write the natural numbers as the set of all ordered pairs. Ordered pair is sort of the only real new concept we need to get from the natural numbers to the integers and rationals. So we're going to say this is the set of all integers divided by natural numbers such that they're relatively prime. That is, if z is AB and n is AC for A, B, C, all integers, then A is plus or minus 1. And then you can go back to your usual notation. Where the ordered pair plus an n we just write as n or plus n, the ordered pair minus n we write as minus n, and the ordered pair n, d, or zn we write as n over d or z over n. And similarly to the integers, working with working with these definitions, you can define addition and subtraction and multiplication on ordered pairs. You can show that everything you know, everything you expect to be true about the integers and the rational numbers is in fact true. And we're going to just assume, we're going to take that for granted. So from now on, you are allowed to assume all the usual facts about integers and rationals are true. So it's just a little bit of work that someone had to sit through and work through at some point, but we're not going to do that. So we're going to just take natural numbers, integers, rationals as given because they're pretty simple. But what we are not going to do is take the real numbers as given. We're going to actually spend a lot of time talking about the construction of the real numbers because the construction of the real numbers is much more complicated than what we've done in this video. In this video, we're going to define something called Dedekind cuts, and this is how we rigorously construct the real numbers. And this is going to be a sort of complicated definition, but as it turns out, it's the simplest thing that we can build up from smaller, easier to understand pieces, and that has all the properties we want a real number to have. So a Dedekind cut is a set A that satisfies all the following conditions. So first off, A is a set of rational numbers. So we said we were building this up out of things we know exist, we understand. We understand the rational numbers pretty well. They're ordered pairs of integers with some cancellation in conditions, least common denominator things. We're going to say we don't want A to be the empty set. You can write that as the empty set is a proper subset of A. It's a subset of everything. We also don't want A to equal the rational numbers. That means that A has to be we said it was a subset of the rationals, but we're going to insist it's a proper subset. So a Dedekind cut is a non-empty proper subset of the real numbers. It has to have the following two more things are supposed to be true about it. If B is an element of A, and if A is less than B, and A is in Q, then A is in A. So a Dedekind cut is all rational. It is all the rational numbers that are not too small. And then here's the last one, which is kind of tricky. Again, we're starting with if B is an element of A, then there is a C in Q, with C is bigger than B, and also C is in A. Now, we don't require all of the rational numbers bigger than B to be in A. If A had all the smaller ones and all the bigger ones, it would have all the rational numbers, which we don't want. But we do require that there be at least one rational number that's in A that's bigger than B. So let's draw a picture of this thing. Here is our number line. Here's all the rational numbers. We've got a point B here. B is an element of our Dedekind cut at A. Then all of these rational numbers over here on this side of B are also in your Dedekind cut. So we can just color that entire line in red. Then there's some number C up here. Then any other rational number in here would be in our Dedekind cut as well. There's our Dedekind cut. So it looks like this. It looks like a half infinite line, everything up to some stopping point. So let's have an example. Let's let A be the set of all rational numbers Q and Q, such that Q is less than, pick your favorite rational number. I'm going to make it 3/2. And then then A is a Dedekind cut. And this is not at all difficult to prove. So three of the axioms are obvious. A is a subset of Q. A is not equal to the empty set because, let's say, 0 is in A. A is not equal to the set of all rational numbers. Let's say 2 is not in A, so we're missing something. If B is in A, and A is less than B, and A is rational, then A is less than B by assumption is less than 3 halves, because by definition of A. So A is also less than 3 halves. Equality is less than is a transitive property in the rationals. We're assuming we know everything about the rationals, including inequality is a transitive property, so that means that our little a is in our Dedekind cut A. And finally, if B is in A, then B over 2 plus 3/4, that's strictly less than 1/2 of 3 halves plus 3/4 equals 3 halves. So C B over 2 plus 3/4 satisfies. C is greater than B, and C is in our Dedekind cut A. Right, cool. And this is pretty much what Dedekind cuts look like. They tend to look like the archetypical Dedekind cut is the set of all rational numbers that are less than your favorite rational number 3 halves. And this would have worked for any other rational number other than 3 halves. And conversely, this set, if we put a less than or equals to sign here, is not a cut. And to show that you're not a cut, you just need one axiom to work. So if we pick B equals 3 halves, that's an element of our set. But any number bigger than B is not an element of our set, so we don't satisfy the last axiom of a Dedekind cut. So we can pick, so Dedekind cuts look like the first example, rationals less than 3 halves, not like this, rationals less than or equal to 3 halves. And this is really the point of the last axiom, to force us to pick this and not this as sort of the Dedekind cut we want to attach to the number 3 halves. One last thing I would like to point out, if you've got a Dedekind cut A like we've drawn in red over on the left, and you pick some point D that is not in A, and you pick some other point E that's bigger than D, then E cannot be in A either. If E was in A, then all the rationals smaller than it would not be in A. I suppose I do have to specify that D is a rational number for this to work. If E was in A, then we'd be able to fill in down like this, and we'd pick up D, and we aren't allowed to do that.